In the last video, we found a process to find the slope of the tangent line using the slope of the secant line and limits. It was very cool. It was very exciting. What I want to do now is to see if we can generalize that process, because last time we found the slope of the tangent line at x equals 1. I want to see if we can generalize the exact same process that we used in the last video to work with just a generic x value so that I could work with multiple x values a little bit quicker. So last time we started by finding the slope of the secant line between 1 and 1 plus h. Rather than use 1 and 1 plus h this time around, I'm going to start with the slope of the secant line between x and x plus h. And if I apply that average rate of change formula, or the slope of the secant line formula, I would end up with something that looks like this. That might look a little bit intimidating. You've got a lot of variables there. We've got a lot of letters going on, but this is just coming from f of b minus f of a divided by b minus a. So it is something that we already know. We're just applying x and x plus h to this formula. So when I plug this in, I'll have f of x plus h minus f of x divided by x plus h minus x. And if I look at that denominator, I see that I can cancel an x. We can simplify it a little bit so that we end up with f of x plus h minus f of x divided by h. So this tells us the slope of the secant line. Hopefully this looks really familiar. If you think back to 2.1, this looks pretty similar to the difference quotient that we had. Here we just have a generic x value rather than a specific one. And what did we do next? Well, we found the slope of the secant line, and then we applied the limit. And that's what we're going to do. And that's what's going to define this really important concept, this really important thing called the derivative. So for some function f of x, the derivative, which is read as f prime of x, we use that apostrophe right there, we say f prime of x, we define that as the limit as h approaches 0 of f of x plus h minus f of x divided by h, which just came from the slope of the secant line. So we're using the exact same process that we used in the last video, but we're just using x rather than, say, a specific x equals 1. And I should make one mention here that if the limit exists, it's kind of a big if. It's not a guarantee that the limit will exist. And if the limit does not exist, that means that the derivative will not exist. And we'll see some examples of that towards the end of this section about what that might look like if our derivative does not exist. So this piece right here is the derivative. This is what's called the limit definition of the derivative. Right now it's the kind of the long way to find the derivative. And the derivative is really exciting. We're going to be talking about the derivative a lot in this class. We're going to talk about it in really for the next 3 chapters. The derivative can tell us all sorts of interesting things. We said from the last video, we said that the derivative can tell us the slope of the tangent line. So we can use the derivative to help us evaluate or find the slope of the tangent line at a specific x value. So that's very cool. The derivative can also tell us instantaneous rate of change. Instantaneous rate of change. And I put that word instantaneous in parentheses because sometimes we use it there, sometimes we don't. If we just say rate of change, then you can go ahead and assume we're talking about instantaneous rate of change. The only other time we would talk about rate of change is if we're talking about average rate of change, in which case we would go out of our way to make sure that we mention that word average. But if you just see if you just see rate of change, that means the same thing as instantaneous rate of change. Lastly, the derivative can tell us the velocity of an object if our function f of x is a position or distance function. So this one doesn't always apply, but it can tell us really interesting things here. So the derivative tells us all three of these three things. It tells us the slope of the tangent line, it tells us the rate of change, and it tells us the velocity. From this point on going forward, I want you to sort of link these three and actually four things in your mind. If I refer to slope of the tangent line, I want you to immediately think of the derivative. If you read a problem that talks about rate of change, you should think about the derivative. If there's a problem that asks about velocity, I want you to think about the derivative. All three of these things, while they're not interchangeable, they are related and they all link back to the derivative. So when you see any of these three terms, just know that in the back of your mind, we can use the derivative to help us find these three things.